guys. I hope we've been good. We've been taking a series on Maths 251 which talks about solution techniques to some differential equations. So far we've looked at the first order differential equations. We've also looked at the higher order differential equations. As a second case, the third scenario, we looked at solving systems of differential first order equations. We are going to take the last technique. That doesn't mean that is the last thing under solving differential equation, but for our aspects of studies, we are taking the last category, that is the Laplace transforms. I'll have it as LT as the fourth technique. So this first video is a motivation to Laplace transformations. As the name suggests, it's a transformation. It is under a group called integral transforms. The whole idea of this integral transform is such that I have an original domain. I want to move to another domain. So this is the original and this is the new domain. The intuition here is that sometimes it's difficult to solve in the original domain, or it is complex. But when you move to a different domain, it becomes easier, or it is simple to solve in this new domain. So transformation T. There are lots of integral transforms. We have the Mellin transform. We have the Laplace transform as we are taking. There's a Fourier transform. So I'm looking at examples. Fourier transformations. We have the wavelet transforms. We have the Z transforms. The Abel or the Abel transformations. The legendary transformations. And a whole lot transformations. All they do is to move the problem from the original domain to a new domain which is simpler to solve. And so if I want to term this original domain as, let's assume there's some f of t, and I want to have this new domain as some big F of t. How do I relate this to positions? And so by definition of integral transformations, I assume that this big or this new transformation is equal to some integral transform of a kernel times the original problem. So it's a convolution or it's a projection of the problem onto the kernel. So this, it is a known as your known problem. This is the kernel. This is your new new solution or new problem. Okay, now depending on the type of transformation you are looking at, depending on these transformations you have here, we can define what our kernel is, and we can define what our integral limit is, AB is. Let me write it here. The type of transformation, integral transformation, will let us know what our kernel is, and then will help us to also know what our limit of integration is. And so with our focus here as Laplace transform, let's take that one. Laplace transform LT. What is my kernel defined? My kernel defined is as the exponential function. And then my limit of integration is defined from 0 to infinity. T here is the time. S is the frequency domain. This is what we have. It means that I can express Laplace transformation. If I have a function f of t, it is giving me big F of s from time to frequency. I can rewrite this as Laplace transform of f of t. These are the various notations for Laplace. And so big F of s, which is equivalent to Laplace transform of f of t, is given as the integral 0 to infinity. The kernel is negative st. times the original problem. This is how you define the Laplace transform. So what I did is to substitute what this kernel is and what this limit are to define the Laplace transformation. Okay. So this Laplace transformation, what we are going to do basically is we have a real problem. We model it as a differential equation. We look at its transformation. And then since we have to do the interpretation into the real problem, it is like doing an inverse transformation. We are going back. Here we've moved from t to s. And so we must move back to what? T. From the s to t. From t to s. And we must move from s to t. And that is the inverse transformation. So the question is, if I have a differential equation, we should note that I can solve first order differential equation with the Laplace transform. I can solve higher order differential equation with the same Laplace transform. I can solve systems of first order differential equation also with the Laplace transform. And to realize that the game here is to know the Laplace transform of functions. Because if I write differential equation as y prime prime plus 2y equal to 0, it means I should be able to find the Laplace transform of this guy. I have to find the Laplace transform of this guy and then solve. How do we do this? Again, I want to say that you realize that if I'm solving, someone will say, I already know the techniques in solving this guy, so why do I want to look at Laplace transform? We said sometimes it's difficult, I want to make it easier. If I have first order ODEs, you realize I have to find, whether say if it's separable, is it exact, is it linear, is it non-linear, is it homogeneous, and I know which one to use. If I have higher order, I have to use some root equation, whether it's method of undetermined coefficient or variation of parameters. This is for non-homogeneous equation. The same applies to the system. And so we want to do away with all these various techniques we've gone through and simply use the Laplace transformation. Again, it means that whatever technique I use, I should get the same answer as using Laplace transformation. And that is the motivation for Laplace transformation for our studies. In the next video, we are going to take Laplace transform of some common functions. Then we can know how to solve differential equation with the Laplace transform. So stay tuned for more lecture videos on Laplace transformations. Thank you.